All right, well, thanks everybody for coming. I'm very happy to be giving this talk. I'm especially happy to be giving it in the presence of Martin Balázs because I learned a lot from his papers with Timo Seppäläinen, and in some sense, this talk is about what we've learned over the past 2 years or 3 years about this coupling method. So we're going to start with a very classical model, not diffusions, the O'Connell-Yor model. So this is one of the first integrable polymer models. And it's defined by this partition function where we integrate over jump times S1 up to Sn minus 1. And what we do is we integrate e to this sum of increments, these Brownian increments. In 2 slides, there'll be a picture that makes it clear that this should be interpreted as a polymer. But at least it's very clear that this is a Gibbs measure, and it's a Gibbs ensemble over these ordered n-1 tuples of numbers S1 up to Sn minus 1. And as you see, it's something like a maximization, but instead of maximization, we replace it by a softmax. So this model, even though I call it O'Connell-Yor, and this is the model that's usually now known as the O'Connell-Yor polymer, it's not actually the model that's in that 2001 paper by O'Connell and Yor. The model that they introduced is this one, where instead of n-1 times, we have an additional time S0 that has a special role because it's in the Hamiltonian, it appears with this linear coupling term, theta times S0. And this is called the stationary O'Connell-Yor polymer. On the next slide, you'll see why it's called stationary. But same idea, we integrate over this n tuple, and we sum n independent Brownian motions, Brownian increments across these jump times. Okay, just everybody clear with the model so far? Any questions? All right. So you see it's the same model, except that we've added one more integration, and we've added this term theta S0 times B0 S0.
Is there a easy way to explain an intuition of what's going on?
Yeah, so maybe in 1 or 2 slides, we'll see what it is. So maybe we can start with this. So what's the idea? In the stationary model, these times S1 up to Sn minus 1 represent jump times. And the way that you can think of this integral is as a partition function for an ensemble of upright paths. So the paths now live in continuous time, but there are discrete levels. So in the model, the LPP model, for example, or the discrete polymer models, we have discrete space, but here we have continuous time. And since we want the paths to be upright, the only choices that we have to make is when we decide to jump, okay, between level j and j plus 1, and this happens at time sj. Okay, and so this is what the interpretation of this model is. It's a Gibbs measure over this ensemble of paths. And the energy that you accumulate from the environment at level j is this Brownian increment. To each level, we have a Brownian motion associated to it. And while we are on the jth level, we accumulate increments of that jth Brownian motion. Does that make sense? Okay, so for the stationary model, for the original, not the original one, but the one that's usually known as the O'Connell-Yor, the non-stationary model, S0, the initial time is fixed at 0. And for the stationary model, the initial time, S0, could extend all the way to minus infinity. And at some point, we decide to jump into the bulk, and then it looks like the non-stationary model. Okay, so these were the pictures. And why is it called stationary? This is actually a consequence of the main result in this paper of O'Connell and Yor. That's mostly a stochastic analysis paper. They show that if you look at the increments of the partition functions across different system sizes, so you look at this system with n levels minus the system with n-1 levels, these increments across n are IID, and they have a distribution that you can compute. It's log of 1 over x, where x is gamma distributed with parameter theta. And this is true for every t. So that in that sense, it's stationary. Okay, so these are the pictures again. Because of the stationarity, because you can represent log of z and t as a sum of IID increments plus the Brownian motion, we can easily compute the first order limit. So for example, for the stationary model, you can divide by n and take the limit as n goes to infinity. You have this theta times t coming from the Brownian motion with drift, and this psi 0 of theta coming from the expectation of log of 1 over x, where x is gamma distributed. If you look at the non-stationary model, it's not just a law of large numbers. This is work of O'Connell and Moriarty. but this is well understood how you can go from the stationary to the non-stationary model. You have to do an optimization problem. So as you see here, you're optimizing the result, the limit in the first case over theta, and then you get the first order behavior in the bulk model. So this is one of the best understood integral models. In particular, in 2009, O'Connell embedded this problem into a triangular array, and he connected it to Whittaker functions, and he showed that it really has this Gibbs line ensemble property that allows you to basically write down a contour integral, or a formula at least, for the Laplace transform of log of z and t. And a slight modification of this formula was used by Borodin, Kollrund, and Ferrari to actually show that once we remove this n times f theta, this first order behavior, and we scale by n to the 1/3, then we get the Tracy-Whittem GUE distribution. So this is using really the full integrability of the model. In 2010, Seppelin and Valco applied the coupling method that we heard a lot about from Martin in the fourth course, which does not require really the full integrability of them all. Actually, it only requires the stationarity, this fact that you can write the increments as that the increments have this IED structure. And they're able to show that the exponents, chi and xi, the fluctuation exponents, take their expected value. So when we look at the variance of the partition function, it's n to the 2/3. This is what we would hope to show in all these KPZ models, but in this case, we can do it. And again, we can do it without using the full, there's no contour integrals. It's just basically the method that we saw. And similarly, there's a certain quantity on the second line that corresponds to the transversal fluctuation exponent. I'll explain this in a moment. And it also has this, the correct exponent, n to the 2/3. And the proof more or less follows the steps that Seppelin took in his 2009 paper on the log gamma polymer, which was a discrete polymer that was actually built from the inspiration that Seppelin got from looking at the semi-discrete polymer that we're talking about. Okay, so just to be clear what the fluctuation exponents are, in my course, I talked about n to the 2 chi being basically the order of the variance, and n to the xi is the typical distance. If you look at the straight line from 0, 0 here to this level here, Tn, and you look at typically how far this path, this constant path, this piecewise constant path is, very roughly, n to the xi should be this deviation. Okay, so n to the xi is the typical distance, and in this model, n to the xi is represented by the time that in the stationary model, we decide to finally join the bulk. So this is S0. Okay? So it's the time, the difference between the origin and the time when we jump into the bulk. It could be positive, it could be negative, but in any case, Seppelin and Valco show that it's over n to the xi in absolute value. And using stationarity, then if you are not happy with just looking at the time when the first jump occurs, you can look at any intermediate level, so n to the gamma. So you can give yourself some gamma between 0 and 1, and look at level n to the gamma, and look at how far the jump between n to the gamma plus 1, n to the gamma, n to the gamma plus 1 is from this straight line gamma times t. And this occurs also roughly around n to the 2/3. Everything okay so far? All right, so when Nowak, who was Christian Nowak, who was Seppelin's student, joined Cornell a couple of years ago, I got interested in this problem, especially in the problem of extending this method to higher moments. So how can you not only control the variance, but also the higher moments on the correct scale? And we did make some progress on this. We showed that all the moments, the central moments of log of z and p behave like n to the 2/3 p plus some epsilon loss, and the same for the absolute value of S0. Okay, here when I write x bar, I always mean the centered random variable. The proof was a fairly complicated iteration, and it exploited a formula for the cumulants of log of z and t. That's a generalization of the formula that you get in the case p is equal to 2. And we found this formula using Gaussian integration by parts, not using this more recent stuff that we'll talk about in a moment. But you see here, there's still a loss of epsilon, and we didn't really quantify what the dependence of the constants was on p and epsilon, and that would be important if you wanted to get the correct tail behavior. This also generalizes to the 4 discrete integrable polymer models. A similar proof. You don't have Gaussian integration by parts, but you can do something similar. Okay, so after a while, we were working on improving this and maybe trying to set epsilon to 0 and quantify the behavior in terms of the constants in terms of P. And in the meantime, there was this absolutely incredible paper of Emrah, Janjigian, and Sepalainen for last passage percolation, where they introduced a new methodology that allowed them to get the correct exponent, the correct upper tail exponent for the passage time in last passage percolation. Okay, so just maybe one remark. When this came out, the new result that you could get from this is you could get localization across the entire path, because since you were able to control all the moments, you were able to do a union bound and show that if you allow yourself an n to the epsilon error, then the path is concentrated along all levels within n to the 2/3 from the straight line. Okay? So that was a new result at that time. But as I said, actually, there is now a new methodology that was introduced, and it relies on this EJS, this Rains-EJS identity, this identity discovered by Rains in the early 2000s for last passage percolation, and reintroduced into the study of the model by Emrah, Janjigian, and Sepalainen a couple of years ago, using a very simple proof that's also important. They gave a different proof from Rains that shows that actually this identity should be true in basically any stationary model. Okay, and part of this talk is going to show you that this is true, and it's true even in stationary models that are actually not integrable. But let's look first at what we get from this in the O'Connell-Yor case. So using this Rains, or using the O'Connell-Yor version of this Rains, Emrah, Janjigian, Sepalainen identity, and using some monotonicity formulas that we'll discuss in this talk, we're able to get the correct upper tail. So it's not just concentration on scale n to the 1/3. It's actually in the moderate deviation range, the same tail as you would get for the Tracy-Whittem distribution. This is a very strong form of universality. It's perhaps even not quite, but it is, in some sense, this is a form of universality that's more robust than the Tracy-Whittem distribution, because we know that when you look at KPZ models and you take initial data that's not narrow wedge, or that's not one of these integrable geometries, then it's not expected that the limit is actually Tracy-Whittem or something easily computable, but the tail behavior is actually stable under this. Okay, so we get both the upper and lower tail, and as I said, I should emphasize that even though the proof we give is quite different from what you see in this LPP paper, the idea to use this Rains identity is really a contribution due to Emrah, Janjigian, and Sepalainen. But what's important for us is not so much that we can do this for the O'Connell-Yor polymer. As I said, they expected that you could do this for the stationary models. It's that the proof we give relies only on monotonicity and convexity properties, so we'll be able to use it in models that are not integrable, for which there is no other way than the coupling method to study them. So here's again what I said. The proof uses this identity by Rains, or the O'Connell-Yor version of this identity by Rains, and importantly, this simplified proof by Emrah, Janjigian, and Sepalainen. And the proof I'm going to give you also applies to the 4 integrable polymer models with a tiny modification. And this theorem is actually a special case. We'll see that this theorem is a special case of a more general theorem about KPZ behavior or fluctuations for interacting diffusions that include the O'Connell-Yor case, but that are not restricted to it, and that include many models that are actually not integrable. The only thing we know about these models is we're able to compute the stationary model, the stationary measure. Any questions so far? Yeah. Well, I'll give you the model, then you'll see an example. So what is such an example? What is that model that I'm talking about? Okay, so one way to look at the O'Connell-Yor polymer is the following. So because the partition function, remember, was this integral over exponentials of Brownian increments, one thing you can do, and this is nothing new, it appears in, I think I saw it from a paper from at least 10 years ago, by Spohn, and perhaps it appears even earlier. If you look at if you take a stochastic analysis approach and you just apply Ito's formula to d of log z and t theta, and you play around with it a bit, then you realize that what you should really be looking at, or the easier thing to look at, is actually the increments, because we know that the increments are supposed to be stationary, right? So we would expect that after a long time, the increments are the well-behaved quantity here. And so if we look at the increments, log of zj minus log of zj minus 1, just to be clear, what is the j? J is the system size. It's how many levels we're looking at. So we're looking at this picture, but for different system sizes. And when we look at the difference, what we find is the system of SDEs. So they're Brownian motions that interact. Because we subtracted them, we see two Brownian motions at each level. And in the case when v of x is equal to e to the minus x, that's you actually reproduce the O'Connell-Ure polymer. But you could actually study the system for any v. For any v, it will turn out that this system has a stationary distribution if it makes sense, but there's absolutely no reason that it is integrable, and probably it's not. Actually, there won't be this connection with the Whittaker functions, and there won't be a representation theoretic interpretation that would allow you to write down an integral counter-integral formula for the top particle. So what is the top particle for us now? If we think about this, if you think about the O'Connell-Ure model in terms of the system, so if we forget that we're looking at this picture as this multiple integral, and I only have this system with v is equal to e to the minus x, then I can reproduce the distribution of log z and t theta, the stationary O'Connell-Ure polymer, by summing the increments and then adding back b0t plus theta t. This b0t times theta t is what I called log of z0. Remember, it's the increments that are stationary, not log z and t itself. And for notational convenience, we wrote log of theta 0t to be b0t minus theta t. So this expression in terms of the RJs, that's what the O'Connell-Ure partition function is. But we could look at the same expression for a general V, and then there's no longer a polymer interpretation. But as I already said, there is, at least formally, an invariant measure. So this is very well known. If you look at work of Yao or Spohn in the 80s, people were looking at this type, or even earlier Harris, people were looking at this type of interacting diffusions already a very long time ago. And it's well known that you can write down an explicit formula for the invariant distribution of it. And this explicit formula involves V, but also involves the parameter theta. Okay, in the case where V is equal to e to the minus x, this is the distribution of log of 1 over x, where x is a gamma distributed random variable, and that reproduces this consequence of the O'Connell-Ure O'Connell-Ure's original result. So if I choose V is equal to e to the minus x, and I take the RJs to satisfy this SDE, and the initial data to be this, this density, then I actually get an object that reproduces a stochastic object, an object defined in terms of SDEs that reproduces the stationary polymer. Okay, the stationary polymer partition function. But we could do this for general V as long as we're able to solve the equations. And this is not completely trivial because if you see here, if you look back at the equations, they involve the derivative of V, but V is e to the minus x. And so the fact that these equations have solutions, if you didn't know that they come from the polymer partition function, is not obvious from the usual theory. The usual theory for ODEs that requires Lipschitz coefficients, or at least some sort of bound for the moments. So you have to do a bit of work, but because there's a stationary measure, or at least a putative stationary measure, usually this can be done. And it can even be done for perturbations of this e to the minus x that still have this exponential growth at infinity. There's another case of this model that is basically entirely computable, and that's when v of x is equal to x squared. Then if you look back at the SDEs, you're going to have linear terms in the SDE, and as we know in this case, we get a Gaussian process, so everything will be Gaussian, and so that's not very interesting. But the thing that is maybe notable is that in this case, the variance behaves like square root of n. So the standard deviation is like n to the 1/4, so the fluctuations are not n to the 1/3. So this class of models includes some models that are not KPZ. If you look at Spohn's work, he has some guess that this is actually the only model of this type that has non-KPZ fluctuations, but who knows? However, what we can say is that this model has KPZ fluctuations. So this is a result with Ben Landon and Christian Nowak, and I'm writing 2021, 2022, because originally in November 2020, when we proved this, we knew how to do the upper bound, but now we also know how to do the lower bound. So actually for general V, it's not quite general V. I have this condition on the derivatives. We don't actually need all these conditions. We just need some of them, but I'm just putting all of them. Note that these conditions are not they're not benign. They actually imply that V actually grows at infinity quite fast, either at positive infinity or negative infinity. So this is somewhat important, but we don't need all these conditions. But this class includes a lot more potentials than just e to the minus x, and it includes also, if you take like the O'Connell-Ure polymer and you take a small perturbation that says 0 at infinity, and small here is independent of n, so an order 1 perturbation of the polymer, so that it completely destroys the integrable structure, we can still prove that the variance is of order n to the 2/3, both in the upper bound sense and in the lower bound sense. Of course, we know that we need some condition, because I told you for the Gaussian case, the fluctuations are smaller if we just look at something that's a quadratic potential. And in passing, a result also gives an SD-based proof of the n to the 2/3 fluctuations for the O'Connell-Ure polymer. So you don't actually have to know that it comes from a Gibbs measure. Any questions about the result? Yeah.
So in random matrices, when you have the Gaussian case or say Wigner matrices, then you can look at the distribution of the eigenvalues. There, that sort of corresponds to having a potential V of x equal to minus x square by 2. Is this? But then you can generalize it to class of V, and you still get.
I mean, this is basically saying, like in random matrices, this would be saying that when you look at the top eigenvalue of a random matrix that's no longer Gaussian, you can show that it lies within n to the minus 2/3 of 2, right? The next step would be, can you show that its fluctuations are actually Tracy-Witten by comparing to Gaussian? And okay, well, we'll talk about this later. Any more questions? All right, so we can get the order, this KPZ order, provided that we have a condition on the, so just to be clear here, what is psi 2? You may not, so psi 1 for O'Connell-Ure, so when V of x is equal to e to the minus x, this is, maybe let's write it as of theta. This is psi 1. This is the derivative of this psi 0 function. And what was psi 0? The psi 0 function is the log gamma function, the digamma function, sorry, the logarithmic derivative of the gamma function. And where did this come from? It comes from the fact that in the O'Connell-Ure case, the normalization, this is the normal, so psi 0 is the normalization constant for these random variables that have this distribution log of 1 over x, where x is gamma distributed with parameter theta. And so if you take this and differentiate it twice, then you get this psi 2 of theta. And psi 2 of theta being positive, being strictly negative is a requirement. Psi 2 of theta will be 0 in the Gaussian case, because in that case, you can compute what psi 0 of theta is. Psi 0 of theta is e to the minus v, e to the minus theta x. So this is just a Gaussian computation. It's just the moment generating function of the Gaussian. When you differentiate it twice, you get 0 because you get a constant. Okay. We can also, in this model, get the correct moderate deviation range. So we can show that the height function, so this W theta and T, has the same tails as the Tracy-Witten distribution, at least up to a constant in the exponent. Okay. And this is different, this is interesting, I guess, because it's a model that's absolutely not only is it not integrable, but we don't even have this polymer interpretation. We don't even have the path interpretation. All the geometric arguments that we talked about when I was describing these heuristics for 2 chi is equal to xi or chi is equal to 2xi minus 1, they don't really apply, at least not directly. Okay, so everything has to be expressed in terms of formulas. And that's going to be the focus of the rest of this lecture. However much time I've left, I think I won't have time to go through everything. But the important thing, and this sounds probably horrible for intuition, but the important thing is that we want to express everything in terms of quantities that are not as ungeometric as possible. Because if we use geometric quantities, then you're stuck with this polymer interpretation. You have to be able to think about the paths, about tracer particles in the ASAP, and in other models, you have to be able to think about geodesics. But here we want something that depends, we want proofs that only depend on some monotonicity formulas and convexity in certain parameters. Yep. Sorry, my shoe is broken, so I'm not walking normally.
So just on like an intuitive level, is there a C in the generalized model?
See?
So yeah, that like the transversal fluctuation somehow. Just
Oh,
along
so
like
in this
Yeah,
generalized
yeah,
model, there
just-
will be an interpretation of C, but it's not geometric.
okay.
So that's the problem. We don't really have paths to think about. In the O'Connell-Ure polymer, the way that C came up is that we did have an interpretation, a path interpretation. So we can consider a Gibbs measure, and then we can just look at the, how much time past 0 or how much time before 0 we take the first jump, or equivalently, because of stationarity, how much time we spend on one level. And subtract from how much time we spend on one level. And this was of order n to the 2/3, and that's what we can call n to the c. But as you'll see, we have to give it, there's a certain quantity that corresponds to this, but we can't really think of paths in an obvious way. I mean, maybe the surprise at the end of this talk is we actually can, but it's not obvious at all. Because remember, we started WNT theta, just to be perfectly clear. So I guess it's more important that people understand the result than spending too much time on technicalities. We just start from the SDEs. There's no more paths. There's no more integrals. There's no more Gibbs measure. Right? It so happens that with these SDEs, with the correct initial data and with the correct choice of V, you reproduce the O'Connell-Ure polymer. But if you take a different V, there's no more paths. And that's why I was talking about getting rid of geometric arguments and finding arguments that depend only on sort of monotonicity quantities that would be as general as possible, and that would actually show how powerful the coupling method is, because that means that all this proof, it also applies in the O'Connell-Ure poly case, but it will apply, beyond that.
Thank you.
Yep.
Thank you. Your conditions on V are unusual, meaning that people who look at potential e to the minus V require V to be strictly convex or strongly convex, whatever. And in your case, you have condition on the first, second, and third derivative. And so I was wondering, is it an artifact of the proof, or do you think?
The answer is who knows, but it is very important. As I said, these conditions are not benign. They imply actually that the potential will grow really fast at infinity. And if you think about it, if you think of like taking a scaling to Dyson-Brandon motion, it sort of makes sense because you want to scale to like a jump function. But I cannot tell you whether if you take a general convex potential, you're still in the KPZ class. This is what Spohn says, but I don't know. But you're correct. It's not a benign condition, but it's also not technical in the sense that the last one condition, I think the condition on the second derivative compared to the third derivative, actually one of our monotonicity formulas, like it reverses and it doesn't work. So there's one step that would not work if you don't assume it.
Thank you. Thank you.
So what kind of initial data do you consider for this SDEs?
For now, everything is stationary. If you're non-stationary, this is what we're working on this. I expect it could work. If you think about the coupling method for the integrable models, using the same type of like quite general monotonicity results, you can work not with absolutely general initial data, but actually for some types of initial data, you can compare the stationary one to the non-stationary one. So this is possible, but I cannot really, I can't tell you like a general result at this point.
I see. Thank you.
So first a comment, in particle systems, you have something corresponding to this V, which is called the hydrodynamic flux. If it has a non-vanishing second derivative, that's when you're in the KPZ class. If it has a vanishing second derivative, but not the non-vanishing third derivative, Herbert Spohn once told me that you're not yet in Edward Wilkinson, so it's not yet like your x²/2 example, but getting closer to there. So it's a different universality class. And when you have a 0 third derivative, as far as I recall from communications, that's when you get to Edward Wilkinson, which is like your quadratic example. So they are genuinely different classes, as far as I understand, at least in interacting particle systems. But I also had a question. So you can get to last passage from polymers by taking a 0 temperature limit. And last passage is kind of a simpler model, maybe. Is there a 0 temperature limit here?
That's a good question. I don't really know. It should be It should be, but one thing to keep in mind, if you go back to the O'Connell-Yor polymer and you put in the beta and you take the limit, then the limit is sort of singular, right? It's not a very nice SDE limit. It can be made sense of, but if you actually go back to O'Connell, he does not really show that the limit is Dyson-Brownian motion. He makes some sort of analogy, and at the very end, after going through all the computations, he gets some formula, and this formula, not the original SDE model, when you take the limit, you recover the formula that you get for Dyson-Brownian motion. But actually taking the singular limit in the SDE system, I think that's like a different project. It's possible and quite likely to work, but you know, I don't want to make any claims about it. Okay, so as I said, I have way too many slides, so I at least want to give you a general sense of what we did. Okay, so I'm going to skip this slide. This is just saying that nobody has noticed this, and I forgot to mention it, but I guess Martin talked about this in detail. If you want to see KPZ fluctuations, you have to tune the parameters theta, n, and t in such a way, or equivalently fixing theta, you have to tune the aspect ratio of this system such that the contribution of the boundaries are roughly matched. If one boundary is much stronger, is much more attractive, then you're back to being Gaussian. And that's what this slide was about. So we can actually prove this. So this condition here is really necessary. Otherwise, you could just get Gaussian and things are even easier. Okay, so let's see how you get the 1/3. And I'm going to use the O'Connell-Yor case to illustrate, but I'm going to give you a slightly different proof from what Sepelin and Valco gave, because I want to avoid geometric arguments. I want to give arguments that use only convexity, or as much as possible, only use convexity. So this picture is something that if you followed Martin's class will be familiar in all mols, you know, stationary LPP or this mol, or you know, the zero range process mols that were analyzed a couple of years ago. You can always write the quantity of interest, in this case the log of the partition function, as the sum of two IID as a sum of two IID sums. So in this case, one of the IID sums is a Brownian motion, but if we want, we can write that as a sum of IIDs with increments of length, I don't know, 1 or roughly 1, as a sum of t over n IIDs. And the first sum is actually a sum of IID log gamma random variables. But even though they fluctuate on scale n to the 1/2 separately, when you combine them, they actually cancel. There's a wondrous cancellation that gets you down to n to the 1/3 fluctuations. And this is what we're trying to understand. That's what we need to be able to understand. And the first step is what Martin did, is write, you know, log of z as r, that's the sum of IIDs plus a Brownian motion minus theta t. The theta t we can forget because we're going to be centering. We take the variance. On the left side, I have the variance of r, the variance of the sum of IIDs, so that's n times psi 1 of theta. And then that's equal to the variance of t, the variance of log z, sorry, plus t, that's the variance of the Brownian motion, plus twice the covariance between the Brownian motion and the log z. And that term, that's the term we need to understand. That's the term that has the n to the 1/3 size. Because the rest is all constant, right? When I rearrange this, I get variance of log z is equal to something of order n minus t. And the only way, unless there's some special extra cancellation between these two terms, but as I told you, we don't expect it, because this n psi 1 theta minus t, it comes exactly from the condition that Martin showed us of trying to balance, you know, the expectation in this direction and the contribution in this direction and the contribution in this direction. So let's just assume that this is n to the 2/3 or even 0. And we still would need to show that the covariance term gives us n to the 2/3. And this covariance term, the way to think about it is it's really a very small, I don't want to make extravagant claims, but the point of view is slightly different from what we see in Sepelin and Valco. We're going to use Gaussian integration by parts to treat it, because the way we want to think of this term is as the reaction of the partition function to a perturbation of the boundary. Okay, on the boundary. And one way to do this, because we're in this Gaussian case, that's why the O'Connell-Yor model is so nice, because you use Gaussian integration by parts. And if we work, you see that in the end, this actually is equal to the expected positive part of how much time you spend on the first level. Okay, so that's like a transversal fluctuation, is how much time you're attracted to the first level, or equivalently, because of stationarity, once you've jumped, how much time you spend on one level. Okay, but why do you get this? Okay, well, that's just Gaussian integration by parts. When we want to take a derivative with respect to a functional derivative with respect to b0t, we can use the Cameron-Martin theorem and turn this into a derivative, a Cameron-Martin derivative, which means taking adding a shift to the drift of the Brownian motion. And you may be wondering, why does the SDO plus appear? Why is it SCO plus, not just SCO? The reason why it's SCO plus is that, even though I didn't really mention this, we're working with two-sided Brownian motions. Okay, so there's a one Brownian motion in the positive part and an independent Brownian motion that really has nothing to do with it in the negative direction. And because we're looking at the overlap with B0T, where T is positive, we get the positive part, SCO plus. And so once you write it in this Cameron-Martin form, it's completely obvious that when you differentiate, you get back, you bring down the SCO plus, and that's it. That's how you get this formula. And actually, if you think about it, you could give similar proofs, like derivative-based proofs of this formula, this Zeppelin and Kato or Baloch formula for all stationary models. Okay, and I think somebody asked, what is the intuition? I think this is one nice way to think about the intuition of this formula. It's that this covariance term, the fact that this covariance term gives you something that's of order of the amount of time that you spend on one level, it's because you can rewrite it as a derivative. It's the sensitivity of the passage time or the I keep forgetting, the free energy to perturbations on the boundary. Okay, so that's very nice. And this shows that, first of all, one way to interpret this, and in O'Connell-Ure, it's especially beautiful because we get SCO plus, not a sum of SCO plus terms, but really just the exact amount of time that you spend on that level. In LPP, you get a sum of however many terms, a sum whose number of terms is equal to the amount of time you spend, but it's the sum of IDs. And in the polymer, discrete polymer case, you have something even more complicated. But in this case, you get the perfect exact version of 2 chi is equal to xi. Okay? The variance is literally equal to the amount of time you spend on one level. Okay, so now our problem is to get n to the 2/3. And one way to get n to the 2/3, if we have 2 chi is equal to xi, is we should find the other relation, chi is equal to 2xi minus 1. Okay, and there is another relation between SCO and z theta and t, at least in this O'Connell-Ure case, and that's just because, and that's a very, it's very classical. It's just because theta SCO appears as a linear term in the Hamiltonian. So that means that theta SCO, that the partition function itself serves as a Laplace transform for SCO. Okay, and when you have a Laplace transform, you can of course use exponential Chebyshev. So we can control the upper tail of SCO in terms of ratios of the partition function. If we rewrite everything, we find that the probability that SCO is bigger than u is equal to the exponential of three terms, minus lambda minus theta u, and then the center difference of log of z and t lambda and log of z and t theta for 2 different values, and then the difference of the centerings, the difference of the expectations. And if you really must think geometrically, the fact that the difference of the expectations behaves like n to the lambda minus theta squared in the characteristic direction, that's curvature. Okay? So now, how do we finish this? Well, if we want to find the correct order of u, this exponent in the exponential, this is heuristic, but it can be made precise. This exponent in the exponential should be, of order little of 1. Say it should be of order 1. Okay, that means that we're just entering the tail of the distribution SCO. So if we just, like physicists, set u is equal to n to the xi, and we try to set these 3 terms to be equal, and use xi is equal to 2 chi, then we find that the perturbation we should apply to the boundary is lambda minus theta of order n to the minus 1/3, and chi is 1/3, and that's it. The reason why why people were not presenting it like this is because you could not make this work until now. You could not make this work because we did not know how to control log of z and t theta minus log of z and t lambda, or the minus of this, on an exponential scale. But thanks to this Rains identity that was rediscovered, whenever I say EJS is Emra, Janjig, and Sepalainen, we now know how to control this. Okay, and so there's some hope of making this work. And if you think about what we've used so far, we did use this exact identity. Okay, but if this exact identity can be somehow made sense of in general, then we might have a chance to make this work for general models. For example, these interacting diffusions. Okay, so what's the solution to? What was the old solution to get rid of this problem? And that solution, that's the solution that, and that's where we deviate from Sepalainen and Valco, is we use convexity. Okay, so I reminded you that theta times SCO appears linearly in the Hamiltonian. So when you take the second derivative of log of z, let me go back so that you can see what I'm talking about. If you take the second derivative of the log of this function at the top here, you're going to get the variance of SCO. Right? So that's the classic. If I take the first derivative, I get the expectation of SCO. If I take the second derivative, I get the variance of SCO. This is always true when you have a Gibbs type measure and you have a linear term in the Hamiltonian. When you differentiate the log partition function with respect to this parameter, you get the variance of that quantity. And so because it's a variance, it's always positive. So that means that theta going to log of z and t theta is positive. More generally, when you take more derivatives, you get the cumulants. Any questions about this? So how can that help us? Why would we want to do this? Remember, we want to get a relation. We have a relation. We have this relation, but we want to get a different relation that also relates. This is one relation between chi and xi. So one relation between the variance and SCO plus. We want a different relation. And this different relation, instead of being exponential exponential Chebyshev, it's going to be convexity. How is it going to be convexity? Well, the second derivative is the variance, but the first derivative is the expectation, right? And what we had in that variance formula was SCO plus. So it's not quite the expectation, it was the expectation of the positive part. But if we did have the expectation, then we could relate the expectation, which is the derivative of the partition function, by convexity back to the partition function. And so we'd have expectation of SCO plus, which was a quantity that we're interested in understanding, and we know was equal basically to the variance. And we could say it's equal to something else in terms of the variance. So we'd have circumvented SCO completely. We no longer would have this geometric quantity. We'd have variance is bound in terms of something times variance. And that's what we want, because then it's the geometry is out. We just have variance is bounded by some quantity times variance. And if this relationship is nonlinear, then we have a chance of actually getting an upper bound for the variance. Okay, so the problem, however, is that we have SCO plus, we don't have SCO. So we need to deal with the error, and that will be one of the difficult things. Because here I'm actually sort of using something geometric. If I write SCO as the positive part plus the negative part plus a cross term, it turns out that the cross term is small. It's smaller than, and the reason the cross term is small is because of concentration with respect to the Gibbs measure. So that means we're going to have trouble if we try to translate it into the SD language. But let's just ignore this. If you're interested in this comment, I can explain this to you, but in some sense, I'm not interested in it because it's restricted to the O'Connell-York case. It's some explanation for when people ask me, how did you know that this term would be small? Well, we didn't. We actually tried until it worked. But then after the fact, Ben came up with this explanation. Okay, so if you believe me that we can replace expectation of SCO plus, which was basically equal to the variance, by expectation of SCO without the plus, then we have something that we can apply convexity to. Just to remind you, why were we interested in expectation of SCO plus? Well, basically the variance is equal to it. And so by an easy, this should be an upper, this should be here an inequality. We're down to finding the second moment of SCO. The second moment of SCO, this is something that we can, that's the derivative of the convex function. So we can bound it in terms of difference quotients. So let's write difference quotients and then center the difference quotients. And then I already told you the centering gives you this curvature, the centering gives you this quadratic term. And then you're done basically, because then you have the variance, which was over here. Remember, the variance is bounded by this. And then we have n to the 1/3 times the variance plus n to the 1/3. And then the only lie here is that there's another term with the variance at a shifted value of the parameters. So we'll have to deal with this. Okay, but that's easy. That's also monotonicity. So this already appears in Zeppelin and Valko. So it might be, oh my, this is integrable. No, it's actually just for monotonicity that you get this. And so once you get this, once you deal with this extra term, so I want to change this eta back to theta, then I really have the variance of theta is bounded by n to the 1/3 times v to the 1/2, the variance of theta to the 1/2 plus n to the 1/3. Since v is non-negative, it must be bounded by n to the 2/3. Okay, and this is something that actually works for very general models. We only used convexity in this dynamical parameter. Any questions about this? Okay, you may be wondering how, I advertise this as explaining where the n to the 1/3 comes from, but then you might be not satisfied because here I actually set lambda minus theta to be n to the minus 1/3, but actually I didn't really have a choice because this n to the 1/3 comes from matching the two errors, one that comes from curvature and one that comes from this difference of variances. Okay, so you have to make this choice, otherwise you don't get the optimal bound. So now how do we generalize this to diffusions? How much time do I have? Okay, cool. So how do we generalize this to diffusions? Well, there is a quantity that corresponds to there is no longer a Gibbs measure, but there is a quantity that corresponds to E theta NT SCO plus, Remember how we got the S0 plus? It was by performing that Gaussian integration by parts. But this we can still perform in the SDE case. And what we get is the derivative of this height function with respect to, it says initial, but it should actually be with respect to the dynamical parameter. So now we just have to set up this partition function and find suitable couplings such that this derivative of the partition function obeys the convexity that we have for the O'Connell-Yor, and then we can hope to do the same, to reproduce the same proof. The difficult part is actually showing that you can go from the derivative just with respect to the dynamical parameter corresponding to S0 plus to the full derivative with respect to both the initial data and the dynamical parameter, and show that this is O of root n theta, and that's more tedious, and I'm going to skip this. Okay. So what about the lower bound? So the lower bound is usually more complicated, and it took us more time. So we want to show that the variance is bounded below by C n to the 2/3. And the strategy this strategy exists in a couple of places, and I think the first time I saw it was this simplified proof of the lower bound by Moreno, Flores, Zeppelin, and Valco in the O'Connell-Yor case. Their idea is to say, okay, I want to bound this probability. I want to bound the lower bound. I want a lower bound for a probability of an upper deviation. And so what I'm going to do is I'm going to change the parameter lambda. So I'm going to stochastically increase the size of the partition function until basically this inequality is very easy to show. Okay, this lower bound is very easy to show using Cayley-Zygmunt. And then I change the measure back. I do a change of measure argument to control the difference. And of course, as usual, this change of parameter will be of size n to the minus 1/3. We'll see that this is what we need to do. So let's first choose, let's just set Q to be equal to this expectation, and then choose the parameter C star such that when we change the parameter theta to lambda equal to theta plus n to the minus 1/3, we move the expectation by n to the 1/3. The reason we can do this is because of curvature. Okay? And then by the Cayley-Zygmunt inequality, we see that we can easily, log of z lambda, as opposed to log of z theta, can easily see deviations of this order from upper deviations above the expectation of log of z theta. And so now what we want to do is we want to change the parameters down from lambda up down to theta, so that and show that we only lose 1/2 factor. Okay, and so how are we going to do this? What does it mean to change the parameters? In the equation, it's very clear. The initial data has a parameter in some coupling. The equations have some parameter, and we can just change them. For the O'Connell-Yor, if you want, you can actually write this change of parameter in this form. There's one parameter that's coupled to the positive part and one parameter that's coupled to the negative part, and the derivatives have the correct signs. Okay, so first what we're going to do is we're going to change the initial data parameter down, and this, by the general monotonicity that we saw before, you're monotone in the initial data, but monotone in the opposite. You're decreasing in the initial data. So if you decrease the initial data parameter, you actually increase the probability. So that's for free. And then the only thing that's left is changing the parameter, the second parameter, the parameter that's coupled to positive times. And then the idea that you always use in this case is you would want to do a change of measure, to use Cameron-Martin. But the problem is that the cost of this change of measure is gigantic. If we take the time t to be of order n and lambda minus theta to be n to the minus 2/3, you're left with e to the n to the 1/3. So that's way too large. What that means is that instead of trying to change the Brownian motion on the entire axis, we should just try to change it in a small region of size n to the 1/3, show that this is enough, and show that the path basically never sees the region after n to the 2/3, right? And so that sounds dangerous if you want to generalize it to diffusions, but it turns out we can do it. Okay, how much time do I have?
10 minutes.
I hope it's okay to have this comment here. The change of measure argument was done in the last weeks of my postdoc in medicine. I didn't like the last passage proof for the lower bound. So it's actually in our ASAP papers. When we did it for simplex fusion, there is the change of measure there already.
Okay, so apparently this, just so everything is heard, this change of measure, as I said, I was not claiming that this is who invented it. This is the first time I saw it. So apparently it appeared in the ASAP.
That's fine, of course.
Okay, so what we need to do is change the Brownian motion in a smaller interval. So we should change to a new partition function that has 3 parameters. one parameter for the initial data, one parameter for that's coupled to positive times up to a certain time tau, and one parameter for after. And if we do this, then we can see that we can write the partition function with two parameters in terms of the three-parameter partition function, where we have now lowered two of the parameters, the parameter far away in far time, the parameter for initial time, and there's just one piece here that's still at the higher value of the parameter. And we can control the difference because the difference can be expressed in terms of this expectation of SCO minus y n to the 2/3. Okay, so this is what's very important is that this step uses only monotonicity. It does not use any, geometric considerations, except for the fact that in the end we express it in terms of an expectation with respect to the Gibbs measure. So if we assume that this term is okay, then we're basically done. The Cameron-Martin theorem argument works, and we have our lower bound. But now we were still left with showing, this assumption here. And this assumption, it's very unclear how you would write it in the diffusion case, because in the diffusion case we don't have a Gibbs measure, but actually we do. So let me just write the two issues. One issue is we still need to show this, even in your case, and the second issue is we don't know what the Gibbs measure is. But this is actually where this Rains-EJS formula will come in. This Rains-EJS formula will allow us to control that term. It will allow us to control that term in a much easier way than was done until now, because we'll be able to directly get exponential concentration on the correct scale for SCO+. Okay, and so they found this result. And for the diffusion directly, what does it say? It says if you take the partition function with a certain initial data eta parameter, a certain parameter, dynamical parameter theta, and at a fixed point, at a single given point of the moment generating, or the exponential moment generating function, you can compute it. You can compute it, and it's fully explicit. So this expression x plus phi eta minus phi theta might seem a bit abstract, but if you Taylor expand, you start seeing a lot of quantities that we know. For example, when you subtract e to the minus the expectation, then you see this second order term is lambda minus theta, or eta minus theta squared times the characteristic direction. So if we assume that this is 0, we get 0, and the next term is a cubic term. So that's where the n to the 1/3 comes from. Okay, and now the final, or one final idea to generalize things to, one additional idea to generalize things to the diffusion case is that so far I kept telling you we don't have a Gibbs measure. We don't know what the Gibbs measure means because we didn't start with log of a partition function. But it turns out that this expression here can act as a Gibbs measure. Okay, this expression is obtained. It's a very easy. Where it comes from is just from solving a certain linear ODE, and this linear ODE comes from taking a certain derivative of the equation in the direction of a given function. And what are the features we need from this? If we take a function f, from this random functional, we call it the Pseudo-Gibbs measure. If we apply it to a function f that's supported on 0 infinity, then this coincides with the Gibbs measure. In the O'Connell-Your case, in general, it's not really a measure, and you cannot, for example, if you start differentiating it twice, then you don't get covariances. But it's not really a Gibbs measure, so you cannot differentiate it again, but it's still a measure with mass less than or equal to 1. And it is still the case that with respect to this measure, we can represent the derivative as SCO plus for any diffusion, even though we did not start with something that was actually a polymer to start with. So we just manufactured this polymer model out of nowhere, and that's what you get. And then here's the important step. Without using Chebyshev, not using any, because we don't know that we actually have a Gibbs measure. So just using monotonicity and actually convexity, we can bound this in terms of ratios of partition functions, or something that looks like ratios of partition functions. And using this, once you have this, you can just use the EJS identity, because the EJS identity is exactly tailored to bounding things like this e to the partition function, not height function at a certain parameter minus height function at another parameter of criticality. So then we get immediately the a to the 3/2, and you conclude the proof of the lower bound for the variance. And then I can't resist showing you the proof of the fluctuations for W, theta, and t, because once you take this point of view of only using monotonicity, it's unbelievably easy. So you start with W and t theta theta, and you upper bound it because we know that the derivative, so we know that we have convexity. So the derivative is bounded by the derivative at the upper level. So we just get this first inequality. If we subtract the expectation and exponentiate, we get this thing, which we can bound using EJS, and this thing, which we already know how to bound. And that's the end. You get the n to the 2/3 behavior. And for the lower bound, you can actually just use positivity. You can drop the integral and get a lower bound. And that's really all it is. Okay, I would like to tell you more about this, but maybe I should stop here.
Okay, great. So any further questions for Phil? And I'm also trying to keep an eye on the Zoom for questions. Getting some cardio in as part of the moderator duties.
Thank you. Thank you for the talk. I just have a quick question. So when you generalize the V, is it easy to see the RJs, they're still independent? Or
Yeah, so it's not easy. The RJs in general are not independent, but for the special initial data, the product form initial data is invariant. So it remains product form for later times. If you take some other initial data, there's no reason why it would remain independent. It's not really easy. It's a pretty annoying computation using the adjoint of the generator.
okay, thank you.
But it is something that's very well known. It's really expected.
Okay,
All right, thanks.
let's thank Phil again.